We've previously focused just on transformations in 2 dimensions. We've seen that a linear transformation can be represented by the 2 by 2 matrix A, B, C, D, and we can find that matrix by looking at what happens to the coordinate 1, 0, where does that transform to, and that tells us the A and the C values here, and then thinking about the coordinate 0, 1, thinking about where that transforms to, and then that gives us these values here. The same principle can be applied in 3 dimensions. A 3-dimensional transformation can be represented by the 3 by 3 matrix, like that. And again, we can find each of these values by considering what happens to the coordinate 1, 0, 0. So that's the x coordinate is 1, y coordinate is 0, z coordinate is 0. If we think about that and where that gets transformed to, that will tell us these values. Then the coordinate 0, 1, 0. What happens to that coordinate? Where does that get transformed to? That tells us the values of B, E, and H. And then finally, if we consider the coordinates when x is 0, y is 0, z is 1, so this is almost like the k unit vector, what happens to that? And that tells us our C, F, and I values. So if we consider a reflection, so let's just focus on reflections for now. You can see I've drawn out a set of 3D coordinates there. And let's say that in this case here, I want to work out what's the matrix that represents a reflection in the x equals 0 plane. So where does x equal 0 on this diagram? So here's my x-axis. Over here the x-coordinates are positive, over here the x-coordinates are negative. X equals 0 is everything here on this plane. So I'm going to try and sort of show you where that plane is. So we're talking about there. Every point here is where x equals 0. It's quite difficult to represent in 2 dimensions on this sheet of paper, but hopefully that's clear what I'm talking about. And that's why this plane here, the x equals 0, can also be referred to the YZ plane. The YZ plane. So this bit here. So let's think about how we can find the 3 by 3 matrix that represents a reflection in this line, in this plane rather. So let's think about what would happen to the coordinate 1, 0, 0, because that's going to tell me what these values here. So the coordinate 1, 0, 0, so that's the x coordinate is 1, and the y coordinate is 0, and the z coordinate is 0. So that's that point there. If that gets reflected in this plane, that is going to get reflected over to the other side over here at -1, 0, 0. The x coordinate would be -1. The y coordinate is still going to be 0. The z coordinate is still going to be 0. So that's going to be the point -1, 0, 0. Now let's consider the coordinate 0, 0, 1, 0. So x is 0, y is 1, z is 0. So that's x is 0, y is 1, z is 0. So not coming out of the page, we're just in the page there. So if I was to reflect that, well, that is on the plane itself. That's on the mirror. So that's not going to move at all. That's an invariant point. So that is going to stay at 0, 1, 0. And then finally, the coordinate 0, 0, 1. Let's consider what would happen to that. So that's the x coordinate is 0, the y coordinate is 0, and the z coordinate is 1. So that's 1 unit out of the page here. 1 unit stepping out of this sheet of paper. Again, that is on the mirror. So that is invariant. It's not going to move. So again, that is going to stay at 0, 0, 1. So this is the matrix that represents a reflection in the x equals 0 plane, or otherwise known as the YZ plane. Let's do another one of those. So a reflection in the z equals 0 plane now. Let's think about what the matrix for that would be. So first of all, the z equals 0 plane, so where is the z coordinate 0? So that's not coming out of the page, it's not going into the page, it is on the page itself. So it is everything in the page here. The coordinate, let's first of all, just like I did before, consider the coordinate 1, 0, 0. What happens to the coordinate 1, 0, 0? Well, that is in the mirror, so that is not going to change at all. So 1, 0, 0. This does not get reflected anywhere because it's on the mirror. The coordinate 0, 1, 0, so that's the x coordinate is 0, the y coordinate is 1, the z coordinate is 0. Again, that point is on the mirror, so it is again invariant. It's not going to get reflected at all. And then finally the coordinate 0, 0, 1, so that's the x coordinate is 0, the y coordinate is 0, and the z coordinate is 1, so that's taking one step out of the page, and that will get reflected in the mirror plane, so to the other side of the mirror plane, going into the page, so this will be -1. And there we go. This is the matrix that represents a reflection in the z equals 0 plane. So just by comparing those two results then, this is a reflection in the x equals 0 plane. This is a reflection in the z equals 0 plane. I'm sure based on that, I hope based on that, you could probably just take a guess about what a reflection in the y equals 0 plane would look like. Hopefully you've guessed it. Like that. Right, so that's reflections in a plane. What about rotations? Rotations are going to be slightly trickier. So again, I've drawn my axes slightly differently in this case here. Still, just to make it a bit clearer what happens to the coordinates, that's the only reason why I've drawn them like that. Remind me to tell you about the right-hand rule for making sure that you always get your axes pointing in the right direction, because it does actually matter. But not too important for this case here at the moment anyway. Anyway, so I've drawn my set of axes, and first thing is to talk about definition when we are doing rotations. Exactly the same way as when we were rotating in 2 dimensions. Anti-clockwise is the sort of definition. When we talk about rotation, it has to be anti-clockwise. But we need to talk about which direction we are facing when we say anti-clockwise. Because if I'm facing forwards, so if I'm facing, so for example, if I was looking along the y-axis here, an anti-clockwise rotation would be that way round. Whereas if I was facing the other way, an anti-clockwise rotation would be the other way. So this, if I'm facing this way, the rotation would be like that. If I'm facing this way, the rotation would be like that. So the direction in which you're facing is actually important. And so what we do is we define it as being when you are facing the negative direction. So let's start off by finding the matrix, the 3x3 matrix that represents a rotation theta around Well, let's do the x-axis first of all. So just like we did before, we're going to consider what happens to the coordinates 1, 0, 0, 0, 1, 0 and 0, 0, 1, and that's going to tell me each of these columns. So if I'm rotating around the x-axis, I first need to face in the negative x direction. So x is positive this way, so I want to be talking about the negative direction this way. If I'm facing this way, then an anti-clockwise rotation around this axis here, an anti-clockwise rotation would be like that. So what that's going to do, first of all, I'm rotating around this axis. So let's first of all consider the coordinate 1, 0, 0. Let's think about this point here. Well, as I'm rotating around this axis, this is on the axis. So this point here is not going to move at all. So we'll stay with 1, 0, 0. Right, what about the coordinate 0, 1, 0? So what about this coordinate here? Well, that is going to rotate. That's going to rotate theta degrees, because remember I'm turning this way. So this is going to turn like that. Again, it's quite difficult to draw this in 2 dimensions, but that's going to rotate like that, where this is theta. So I'm basically saying like that. That's what I'm trying to draw here. Gets rotated like that. Now, remember how we did this in 2 dimensions? That is 1, because this length here was 1 to begin with. So just rotating it will still be 1. And what I'm interested in is what's the x, the y, and the z coordinates of this point here, because that's going to tell me this column. So, by drawing a little right angle triangle here, I can work out this length here, because this is the adjacent to the angle. So I can say cos theta is equal to the adjacent here, which is what I want to work out. This is going to be my y coordinate here, how far along the y axis I am for this, divided by 1. That's the hypotenuse there. So, and that is just, you can just see now that the y coordinate is going to be cos theta. By the way, I should have mentioned this first, the x coordinate here. Notice we're talking on this line here. Like I said before, this is representing this point getting rotated around. The x coordinate here, how far I was along here, is still 0. So the rotation isn't going to move this along here, it's just going to rotate it around. It's not going to move it along the x-axis, so the x-coordinate will still be 0. The z-coordinate, that is how far it's gone up. So this here, that's the opposite side, that's the z here, and that's going to be given by the sine theta, because opposite over hypotenuse. So we can see here that the z will be sine theta. So we'll get 0 cos theta sine theta. And for the final column, I need to consider what would happen to the point 0, 0, 1. So that's when the x-coordinate is 0, the y-coordinate is 0, and the z-coordinate is 1. So this point here. And remember that we are rotating that way, rotating this way around. So this point here is going to rotate and be like that. So again, it's quite difficult to draw this. It's going to rotate theta like that. Again, this length there is 1. And similarly as before, I want to work out this coordinate. Let me put it up here. So the x-coordinate of this point is still going to be 0 because it was originally in this YZ plane, and it's still going to be in the YZ plane when it gets rotated. It doesn't move out of the plane, it stays in that plane, so that is still going to be 0. The y-coordinate, now I noticed that I'm actually in the negative part of the y axis now, so I know that this is going to have to be negative here, and I know that that's going to be the opposite side of this right angle triangle, and we know the opposite comes from the sine, so that's going to be minus sine theta. The z coordinate here, that's going to come from the adjacent, so that is cos theta. So that is our third column here. So there we go. This is the matrix that represents a rotation theta around the x-axis. I know it's quite complicated to see where that's come from, especially when I'm doing a three-dimensional drawing in 2D. Hopefully we'll get back into the classroom as soon as possible and I can actually show you this in 3 dimensions because it is a lot easier. Anyway, I'll do another example. So we've done rotation around the x-axis. What about rotation around the y-axis now? Let's do that one. And then after that, I'll show you a little pattern that will help you identify them more easily. So rotation around the y-axis. So I need to be facing the negative y direction. So the positive y direction is that way. So the negative y direction will be this way. So if I imagine facing, if you imagine you're stood here and you're facing this way, an anti-clockwise turn would be this way round, would be turning like that. So stood facing this way, and it would be facing, it would be rotating like that. So let's consider what would happen again to the coordinates 1, 0, 0, 0, 1, 0, and 0, 0, 1 to get these 3 columns. So the coordinate 1, 0, 0, as that rotates, as I rotate around, this is going to rotate downwards, because as I'm rotating this way round, so it's going down theta like that. Again, that's 1, just like before. If I draw a little right angle triangle, I notice that the x-coordinate of this point here is represented by the adjacent of this right angle triangle, so that is cos theta. The y-coordinate, now the y-coordinate of this point, it's still in this plane here. So the y-coordinate here was 0, and moving it down slightly affects the z-coordinate but doesn't affect the y-coordinate, so that is still 0. The z-coordinate, I notice that that is negative now. Remember, this way is positive, so it's gone down. So I know this is negative, and it's represented by the opposite side of this right angle triangle. So that is that. Now considering the coordinate 0, 1, 0. Well, this is along the axis of rotation, and like before, when I rotate around this axis, that's not going to affect the axis itself. So that point there will not change at all. It is invariant. And now finally, let's consider the coordinates 0, 0, 1, and think about what would happen to that. Again, as I'm facing this direction and rotating anti-clockwise, this is going to move and rotate to here. So it's like coming that way. So this one here went down into the page like that. This one here was like that. So let's consider the each of these points then. So I'm looking here and I'm seeing that the x coordinate, well actually let me mark on, remember that length there is 1. So the x coordinate is coming out of, it's coming this direction, which is represented by this opposite side here. It's in the positive x direction, so it is just going to be sine theta. The y coordinate is just going to be 0. It was 0 here, and rotating it like that in the plane will not change the y at all, so that'll still be 0. And the z coordinate, that's represented by the adjacent side here. It's still in the positive direction, so that's still cos theta. And there we go. Like I say, I hope that I am able to show you these in 3 dimensions in the classroom very soon, but I hope that these diagrams and those quite long explanations have helped a little bit. Anyway, to show you all 3, so we've done x and y. I won't do z, but z looks like that. Now, I'm hoping you kind of recognise this cos theta minus sine theta cos theta, because that was a rotation in 2 dimensions. So let's just look at each of these. This was the rotation in 2 dimensions. We're used to this, we were given it in the formula sheet and we dealt with it a couple of lessons ago. And then this 1, 0, 0, 1, 0, 0 here is telling us it's in the x-axis. Here, this 0, 1, 0 and 0, 1, 0, this here and here, that's telling us it's in the y-axis. Again, we've got the cos theta, sine theta minus sine theta. So notice how the signs here have flipped. And then finally, this and this is telling us it's in a rotation around the z-axis. And then again, we're back to the original cos theta minus sine theta, cos theta. So these things look quite complicated to begin with, but actually it's just an ever so slight extension to this. Okay, let's look at an example. So we have got a matrix M there. Part A says to describe the transformation, and then part B says to find the image of this point under the transformation. So straight away, by looking at this, I'm seeing the 0, 1, 0 and the 0, 1, 0 across here. I'm thinking this is probably a rotation around the y-axis. And then I'm comparing this to the standard formula. And so I'm thinking that cos theta is my root 3 over 2, and sine theta equals a half. And that seems to be consistent. If sine theta is a half, then minus sine theta would be minus a half. And again, we've got the cos theta, they're the same as well. So if cos theta is root 3 over 2, then I know that theta is 30, my principal solution from doing cos inverse of root 3 over 2. And then I can check the cos graph to see that 30 from here, 30 from here, I'll have another solution at 330. So these are my 2 solutions for cos theta equals root 3 over 2. And then I also know that sine theta equals a half. So that tells me if I do sine inverse of a half, I get 30. And then using the sine graph, 30 from here, 30 from here, I can see there'll be another solution at 150. Which means in order for these to be consistent, theta must be 30. So this transformation is a rotation around the x-axis, the y-axis of 30 degrees. That's what this does. And if I apply this to this image, to this point, this coordinate here, if I rotate this coordinate 30 degrees around the y-axis, it becomes this. If I multiply these two together, I get this. So basically I'm just doing root 3 over 2 times minus 1 plus 0 times minus 2 plus a half times 1. That gives this. 0 times minus 1 plus 1 times minus 2 plus 0 times 1 gives this. And then that gives that. So we're saying that when I rotate this 30 degrees around the y-axis, I get this, which should hopefully make sense. You can see the y-coordinate there is has not been changed because we're rotating around the y-axis. Obviously the x and the z have been changed. So there we go.